Okay, welcome to everyone to the tutorial ESP, an open source platform for Agile SoC development. My name is Luca Carloni. I'm a professor with the Department of Computer Science at Columbia University. And today we'll, together with part of the ESP team that I'll introduce in a second, we will tell you about our research and how our research has produced this project, which now is open source, has been open source since last year. Next slide. So the tutorial, this is the agenda of the tutorial. We'll have an introduction, which is about the motivation of our research and the reason why we develop OpenESP. And then after that, we will go through a series of hands-on tutorial, building up one on top of the other, and to illustrate the various capabilities of ESP. So you will be able to, if you have downloaded and completed the preliminary setup, you will be able to follow some of this tutorial online as we progress it. So as you can see, there are 5 main segments and a demo, which maybe next slide we can go. I know, hold on. Okay, see. So we will go through how with ESP you can design and integrate a System C accelerator using a commercial high-level synthesis tool, Stratus HLS from Cadence. Then we'll show you how you can build SoC by integrating third-party accelerator, and we'll give you the example of the NVIDIA NVDLA accelerator for deep learning. And then we will go through how ESP simplifies the integration of multiple heterogeneous component, processor, and a variety of accelerator to do design and testing and FPGA prototyping. Then we will go through one of the multiple design flows which are available within ESP. In particular, this is a design flow specialized for embedded machine learning, which allows people to specify neural network using one of the most a variety of common framework for embedded machine learning, for machine learning in general, like Keras, PyTorch, EONNX, and from that derive automatically by means of high-level synthesis and accelerator and integrate it into a complete SoC. The next step is to show how we can design integrate accelerator with a different commercial high-level synthesis tool, that is Catapult from Mentor. And then we are going to give a demo which will illustrate how ESP can be used, for example, to do research on certain important topics in computer architecture. In particular, we will show you how we have used ESP to build a solution for reconfigurable cache coherency for accelerators, how we can dynamically change the cache coherency model of accelerator in a system on chip. All this will be done by over the next 3 hours. The team, which I'll introduce in a second, it consists of myself and in particular Davide Giri, who is a PhD student at Columbia University, Giuseppe Di Guglielmo, who is an associate research scientist at Columbia University, and Paolo Mantovani, who is an associate research scientist at Columbia University. Next, before we start the introductory part of the tutorial, I think Davide wants to check 1 second and show to each of you who may have not done already the preliminary setup, how you can do the preliminary setup of ESP right now.
So many of you, most of you probably have seen our tutorial page. We have a section with some instruction for preliminary setup. Many of you maybe have gone through it. This is necessary if you want to follow some of the steps of the tutorial, specifically these 3 parts. These 3 parts here are the ones where you will be able to do a little bit. So if you haven't done it yet, probably a fast solution is to just download the Docker image while we go through the overview tutorial. You have the instructions here. It should work for Windows, Mac OS, Linux. So the main idea is download, pull the image, and then run it with this command for Linux, and then there are instructions for Mac OS and Windows. So if you haven't done it yet, maybe now you have the chance to do it. It shouldn't take too long. The main thing is that we need to launch a GUI from the Docker. So there's a slightly different setup than usual. You see here some parameters that we're passing, and you see that on macOS you need exports, and on Windows 10 you need this Windows X server. So that's the idea. While I'm here on this website, I can also introduce you to the ESP website. We have a main page that gives an overview of the project. You see this is an overview. There is an overview paper listed. We have a documentation, a resources section where you have documentation. This is where you find all the hands-on tutorials, and some of this material is something that we will cover during this tutorial. We have a list of publications, tutorials, talks, and teaching. In particular, if you need to contact us for anything, this is our email. And at the end of every page, you have GitHub, Twitter, YouTube, and our website in case you want to know more. Of course, we are already on GitHub as people on the So yeah, this is for the setup. Now I give the presentation back to Luca, and he's going to start an overview of the
So before we go to the next slide, maybe Davide, we want to say that the tutorial will be, as I said, a mix of different segments, as I show you with the agenda. And so you should be able to follow most of them. As we move along during the day, we will tell you what can be done online. But as Davide said, we have many hands-on tutorial available on the ESP website and more material. So there's also I guess many of you can see today as an introduction to ESP and the ESP open source project. And then you can also, if you're interested, complete some of the other tutorials offline after today. So I don't know if there is anything you want to.
Yeah, even if you're not trying the tutorial now live, the pace of the tutorial should be good to follow. Just for watching it, and then you can try later. There will be a recording and we have material.
Okay, so let me give you a little bit of an introduction just to why we develop ESP. And really, ESP, as I said, is an open source project, has been an open source project since last year. And we continue to add new features and do active research using the infrastructure ourselves and continue to improve it. But ESP is the result of over 7 years of research at Columbia University. And so our research really has been motivated now for the past 7-8 years by the consideration that the information technology industry has really entered the age of heterogeneous computing. And pretty much across a variety of computing domains, from embedded system all the way to data centers, you have that systems are more heterogeneous in the sense that they combine components which have different natures. What that means is that you see more and more systems that combine various types of general purpose processor together with specialized processor, GPUs, but also a variety of specialized hardware accelerators. And so heterogeneity happens because it provides superior computing, better computing, both in terms of energy efficiency and performance compared to executing just a software on top of general purpose processors. And so as a result, however, heterogeneity also makes the process of design, validate, and program systems more complex. In particular, at the core of many computing systems, you have the system on chip, which is illustrated here by this figure. The system on chip nowadays is really increasingly a complex mix of many different components. It's typically for high performance embedded system or for data center application, a system that is a multi-core with multiple general purpose processor cores. But next to the multiple general purpose processor cores, you have a variety of engine, some programmable, some configurable, many increasingly specialized hardware accelerators, which provide better performance for particular kernels, the computational kernels that are very important compared to executing in software. So the fact that you have all this variety of components complicates the design effort, the programming effort. And so there is a need for automating hardware-software integration, a need to support engineers and engineering teams for designing and validating components at different level of abstraction. Some components make sense to design them at the register transfer level, starting, for instance, from Verilog or VHDL. Others, we argue and promote different system level design methodology, which start from higher level abstraction, like C system C, or as I said, for some application domain, for instance, embedded machine learning, even higher than that with these frameworks like TensorFlow. Another thing is that systems are complex, have a lot of components, and so is increasingly strategic for companies, but also for research in academia to reuse components. So not to reinvent the wheel whenever you build a system, but really combine components that have designed and validated by others. Conversely, when you develop a new component, sure, in many cases, you may want to specialize it for a particular system on chip. But in other cases, you may want to have a component that is highly reusable across different instances of system. So in this context of the need for design for usability, there is now the growth of the open source hardware movement, of which I'll tell you in a second a little bit more, which really can support the proliferation of the design of many reusable IP blocks. But on the other hand, you need platforms that simplify the integration of components designed by different teams for different purposes. And so I will tell you in a minute, I'll give you a definition of what a platform is, but really ESP is an example of such platform. ESP is a platform which combines a flexible computer architecture with a scalable design methodology, which accommodates a variety of design flows, and which simplify the integration of intellectual property blocks and other components, but designed by different teams. So let's 1 second say one word about the open source hardware movement. I think many of you are familiar. We really believe that open source hardware is an opportunity to re-energize the innovation in the semiconductor and in the electronic design automation industry. It's also a great opportunity for academia to promote research which looks at the system level in terms of really looking for solutions that allow you to simplify the design, the program, and the validation of such system. And so the open source hardware community is gaining momentum. There are a variety of contributions from both academia and industry. And as you'll see through the rest of the presentation today, we actually take advantage quite a bit of components designed by other teams. And at the same time, we contribute with ESP, trying to support open source hardware. And really, what is the need that we think we identified and that ESP addresses is the fact that while there are many other open source hardware projects which are focused on the development of individual SoC components, like individual processors or accelerators for certain purposes, ESP is a little different because ESP focuses on simplify the integration of different components. And so it does that with the concept of platform. So platform is a buzzword in our industry, which has many different connotations often. So for us, a platform is defined as the combination of an architecture intended as a computer architecture and a methodology intended as an electronic design automation methodology, so a CAD methodology, computer-aided design methodology. So a platform is an architecture and a methodology. And so the importance of platform is because architecture and methodology must be developed together in order to be effective. In other words, an SoC architecture enables design reuse when it automates the integration of many components that are independently developed. Conversely, an SoC methodology enables design collaboration when it allows designers to choose the appropriate specification language and level of abstraction to design a particular component. The different components may be designed with different languages, starting from different level of abstraction and leveraging different tools. So, in our opinion, an effective combination of an architecture and a methodology must provide an agile flow that can enhance the potential of open source hardware. And in fact, you'll see how we develop the architecture and the methodology together, and how the methodology, in fact, embodies multiple design flows, which take advantage of tools available from academia and also commercial tools, which, of course, in order to run them, you need to have access to the licenses. So now that we have defined the concept of platform, let's see, I'll say a few words about ESP. So, as I said, it's an open source platform. We show you already the website. Let's go back to the characteristic of the ESP platform. 1 second. The characteristic of the ESP platform is that it combines a scalable architecture and a flexible design methodology. So the scalable architecture, as you'll see, allows you to really do rapid system-on-chip design and FPGA prototyping of fairly complex SoC, at least fairly complex, I would say, from the viewpoint of what you can be realized in academia, by combining components that you can design new from scratch using one of the many design flows available within ESP, as well as components that are available in public domain as open source hardware blocks. The flexible methodology guides designers through the development of the new components. In particular, a big emphasis of ESP is on simplify the design space exploration and synthesis of specialized hardware accelerator, and simplify their integration into the complex system so that you can validate accelerators in the context of a complete system running complex workloads on very large data set. And of course, you do this taking advantage of FPGA prototyping. So I guess we now maybe is the right moment for me to introduce Paolo Mantovani, who is I mentioned before. Paolo is the chief architect of ESP, and so he will take over and introduce the various parts of ESP before we go into the more hands-on part of the tutorial today. Paolo?
Yeah. Okay, should be able to see my screen, right?
Yes, correct.
Okay. All right. So now we're moving a little bit into more of the details of the architecture and the methodology that Luca has just introduced. So first of all, the architecture is meant to scale up. We said that we want to integrate more and more accelerator, more and more heterogeneous components. So it has to be inherently scalable, and that's why it's based on a network on chip. And the network on chip is really at the heart of the architecture of ESP, and it connects 4 main type of tiles. One type of tile is the processor tile, where you can integrate a common CPU. At the moment, we support 2 types of CPU, Ariane 64-bit RISC-V, or a Leon 3 32-bit Spark architectures. And these usually come with their level 1 cache. You may have accelerator tiles, which can be new components that you develop using the ESP methodology, or components that existed already, accelerator or processing engine that you bring in as your jewel, thing that differentiate your idea of system, your specific system or application from everybody else. It can be a memory tile, and we'll talk a lot about memory because access to main memory is one of the main issue, and is probably the most precious resource on the system. We need to access memory as quickly as possible, and we want to save as much energy as possible when we do so by, of course, leveraging the cache hierarchies whenever possible, and any other form of on-chip memory. And finally, we can have an auxiliary tile, which is what allows us to debug our system, to interact with our system. So you will have all of the shared peripherals like Ethernet, UART, video output, timer, and the interrupt controller that are needed to run your full system and your prototype when you test your own accelerators. Now, the most interesting tiles here are the processor tile and the accelerator tile, which are based on sockets. And by socket, we really mean an interface that can host a component. It could be a third-party IP or a new component that you develop that you bring into the picture here. And these work, of course, by using standard bus interfaces, but also by leveraging aggressive automation to generate the appropriate interface for the new component that you develop, starting from high-level synthesis rather than domain-specific languages or even RTL. So basically, there are a lot of automated flows that I'm going to show in a second that will allow you to bring your component into these types. Now, these sockets do not only implement interfaces, but in fact, they implement what we call platform services. And platform services really are all of the things that designers typically have to think about when they design an SoC. Think of memory access, coherency, IRQ delivery, power management, so performance monitoring. So all of these are implemented as services that the accelerator integrated through the socket can access without having the accelerator designer think about them. And some of them offer runtime reconfigurability options. Like, for example, we'll show a demo about on-chip coherency for accelerator, where we can change the runtime every time we invoke the accelerator, the type of coherency that they're going to use. Now, just to briefly, move from the architecture to the methodology, in this slide, we are really showing the vision of ESP. So the methodology that we advocate for is what we see as our vision, which is not only expert SoC integrator, expert SoC designers, but also IP designers, also algorithm developers should be able to quickly test their new IP, their new algorithm in a real system with real workloads and see how they perform in the final system. So we offer a bunch of accelerator flows that can start from different languages. Could be RTL, like System Verilog, Chisel, or VHDL. It could be high-level synthesis, ready languages such System C, C or C++ through commercial high-level synthesis tools. Or, and in this slide, you see for the important domain of machine learning and deep learning in particular, it could be a model written through one of the machine learning frameworks like Keras or PyTorch. And then through the combination of ESP and another open source project, which is HLS for ML, we are able to automatically generate accelerators. Now, from all of these flows, what you obtain is a library of components. And for each component, you may have multiple views, especially if you select the HLS-based flows. And by views, I mean multiple design points that strike a different balance between area and energy cost and performance. So you have a bunch of different components with the same functionality that can all be seamlessly integrated into a system instance. And together with them, our automation system also generates device drivers for you, offers and exposes an API to user space application, and generates a skeleton for the test application that you're going to use to test your IP when you first integrate it into the system. Then from there, there's a series of push button steps that you will have to follow to, first of all, make your floor plan. And this is guided by a graphic user interface that we will show during the tutorials later. And here you can really mix and match your components and decide which accelerator, which processor go in each tile, where the memory access points are, and where your auxiliary tile is. And then by just running a few make targets, you'll be able to get in a few hours just the time for Vivado to run your FPGA prototype ready to execute, both bare metal application and Linux applications. And in the SoC flow of ESP, this graphic user interface that you see here is really at the heart of the system composition. So as you can see, you can select each tile very easily. And for each of the accelerator tile, you get the option to choose which HLS implementation you want to select. And usually that's the result of leveraging different HLS pragmas. So, you know, you may want a version that runs very quickly, but consumes a lot of energy, as well as a version that is a little bit slower but saves energy, right? And so through the graphical user interface, you can switch between one version and the other. You can enable the cache coherency, change the processor selection, and enable performance monitors. So we have a lot of flows, but there are two main classes. And in fact, one class contains all of the flows for the new accelerator, which is something that you want to develop using, for example, a machine learning API, C++ with high-level synthesis or RTL. And in this case, these flows go through these common steps. You first generate the skeleton of your accelerator. Then you have to customize this skeleton by basically implementing the actual behavior of the accelerator. And this step, for example, is automated, though, when you choose the deep learning domain-specific language as a starting point, because you're not the designer of the accelerator specification itself, but you're the designer of the deep learning model, of the neural network model, for example. Once you've done this customization step, you just generate your RTL or multiple RTL implementations using high-level synthesis. And then you can run our unit tests that have been generated together with the skeleton. The second class of flows that you can use is to start from an existing component, so a third-party accelerator. Now, in this case, what we ask the user to do is to define the accelerator, so give it a unique name and a unique ID, and then just list the source files, both RTL and software, together with the make targets. Then from those make targets, you will generate the objects to program your accelerator. So in this case, we just let the user run their third-party software that is necessary to program the third-party IP. So even the objects have to be listed. And then the only manual step here will be to complete a very simple RTL wrapper that leverages standard bus interfaces like AXI, AHB, or APB. And we plan to expand the number of interfaces that we offer to users to really just connecting the wires. So you take your IP, connect the wires to the expected AXI or HB interface, for example, and that's pretty much it. This RTL wrapper doesn't need to contain any logic unless the accelerator requires some non-standard operation to start. Now, from both these flows, we merge into the same SoC flow, where we build our software, configure the SoC, we can run full system simulation or get our FPGA prototype up and run our applications that we've been generating before. So all of this SoC flow is almost completely automated, and we'll show you a few examples later. And again, this is completely independent whether you start with a new design or if you have already an accelerator, meaning that when you move to the SoC flow, all accelerators and IP components are seen as building blocks that have the same importance, that have the same type of flow to then integrate it into the system. So where is the magic? We've talked a little bit about these platform services. So if we look a little more into the details, for example, of the ESP accelerator tiles, we can see a few major components. So we have an optional private cache, and that will handle all of the coherency transactions that we want the accelerator to have with respect to the system and be consistent and coherent with the private caches of all processor cores, but without having the designer of the accelerator know anything about the coherency protocol in ESP. So the designer will only have to issue a memory transaction, and then this optional private cache that can be enabled from the GUI will translate that into a regular cache message for the last level cache. And then it will be, the coherency will be handled transparently. At the same time, we have a DMA engine and a transaction Lucas hide buffer, which is a special TLB actually. It's not the regular TLB that you would find in processor cores, but these combined allow the designer to forget also about physical addresses. So the accelerator can operate in its own virtual address space. And the virtual address space for the accelerator is built by a combination of hardware mechanisms, so this little TLB, and the device drivers that we provide with ESP that basically allow the user to access any storage element in their accelerator by, for example, using indexes. And we'll see the example in the first tutorial. And we have a proxy component to configure registers. So the configuration registers are implemented inside this wrapper and are user-defined. And then we have a component to deliver interrupts. Also, it's not shown in the picture, but there is the possibility to run per tile dynamic voltage frequency scaling. So we've integrated some logic to handle the power management of the tile, based, of course, on a combination of monitoring what's happening on the system. So we monitor the NOC routers to see the traffic and what's the policy being set from the operating system. It's also worth noticing that we have an automated tool to generate the scratchpad of the accelerator, what we call private local memory. So it's not accessible by the processor core, but this is very important in combination with the HLS pragmas, because when you design your IP, oftentimes if it's an hardware accelerator, you rely on aggressive parallelism of the data path. And this parallelism must be sustained by equivalent parallelism in accessing data. So this local memory will have to be tailored to your data path. And the way we do so is we ask the designer to tell us what are the kind of accesses in this local memory. And then we generate, using the available SRAM banks for the target technology, we generate a subsystem that has enough memory ports to sustain the parallelism of the data path. And in the tutorial, we will show briefly this file and how to specify different transactions on the memory. Okay. Now, when you integrate a third-party accelerator,
Paolo?
Yes, do you have a question?
Sorry if I interrupt. There is, I guess this is the first question, technical, related to what just got presented. Can you elaborate a bit on the interface to the local memory from the accelerator? I don't know if you want to take it now or do it later during the demo, but once
I can take
more
it now.
information on the interface. In general, just a second. In general, this is great, guys. Just put your question on the Q&A, and we'll try to monitor and decide when to answer. All the question will be answered, of course.
Yes. So differently from the caches and from the external memory that we access through this read or write port that gets generated when you generate the skeleton of the accelerator, the private local memory is really built in with the accelerator. So for example, if you are using an HLS-based flow and you are coding your accelerator in C, this private local memory from the designer viewpoint will be represented as an array. And in your code, you will just access this memory by using the index as usual. So you will just think of it as an array. At the same time, when we implement this through high-level synthesis, we need to map it to real memories. And typically, technology vendors only provide dual-ported memories at most. So what happens here is that if you, for example, decide to unroll a loop during the HLS step and have some processing engine being multiplied, right, to operate in parallel, you will need to feed these multiple engines with a lot of data at the same time, right? But a dual port memory might not be able to sustain this bandwidth. So what we do here is to take the available dual port memory in the technology and generate an actual memory subsystem with as many ports as your code needs during the HLS mapping step. So you don't have to worry about the interface because the HLS engine is going to map the array accesses to the memory. But what we do is generate the memory view for the HLS engine, for the HLS tool, so that it can use that memory to map an array to it. So this is more an intrinsic communication. It's not an explicit interface in this case. So as I was saying, moving on to the third-party flow, we still use an accelerator tile, but our socket degenerates a little bit into a slightly simpler component. We keep, for example, the interrupt delivery service because we still have to deliver interrupt to the processor cores and to the interrupt controller. But all of the DMA engines and the caches collapse into a bus interface. The reason is usually when you take a third-party IP, the way it interacts with memory is already coded within the accelerator. And this is, for example, the case of the NVIDIA deep learning accelerator that we will show later. So the accelerator will just ask for an explicit physical address in memory, right? So we need to let the accelerator make a transaction on the network on chip of the system that directly indexes some element in main memory. So to do so, we offer a few standard bus interfaces, and we really plan to expand this list so that users can just take their existing accelerator and connect their accelerator's interface to these buses. And then everything else is handled by the socket again. So all memory requests will be translated into NOC packets automatically. Now, one important thing to notice here is that because we expose these bus interfaces this way, in a transparent way, we allow users to keep controlling their third-party IPs with the existing software. While when you design a new accelerator, we provide an API through ESP, and we generate a test application that simplifies the programming of new accelerators. In this case, of course, you already have your software that comes with the accelerator, so it does make sense to simply compile it for the target processor core that you integrate in the system and run the third-party software as is.
Paolo, before you move
Yes.
to the next slide, since this picture, which is for the third-party accelerator, shows that in this particular case, the AXI bus and APB bus. There was a follow-up question on the previous about the interface by Antonino, saying, and the ports to the memory are AXI. So maybe you want to clarify the difference between, for new accelerators, the interaction between the PLM and the data path versus the role that the buses play when you integrate an accelerator like a third party, because the answer is not necessarily, they are not necessarily AXI. Paolo, please.
Correct. So for third-party accelerators, we do have bus interfaces, so like AXI. And in this case, you don't directly access memory, but you access our proxy components that translate the AXI request into an NOC packet that will reach the appropriate memory tile, and so the appropriate split of the last level cache, for example, or go directly in memory if it's a missing cache, and return the data required by the accelerator. Now, when we have a new accelerator instead, this interface is just simple read-write queues that are generated with the skeleton. And this is how the accelerator can read data that are shared with the processor cores. So data and other accelerators as well. So they can be in the cache hierarchy, they can be in memory, depending on the type of coherency model that we want to select when we invoke the accelerator. But those are data shared with all the components in the system. And here the interface is not AXI. It's a custom interface that we've built and that we generate when we run our automated scripts to create the skeleton of the accelerator. The private local memory instead is, as I said before, built into the accelerator. So the interface here is like an SRAM interface. So you will have address, data, enable, write mask. But you don't have to code this interface yourself, because it's the commercial high-level synthesis tool that implements that interface and implements the control logic to access the memory. What we do is we provide the high-level synthesis tool with the memory that does not exist from the vendor. So the vendor library gives you single port memory, dual port memory, maybe register files with 3 ports at most. But you may need to access 8 elements at the same time with a specific access pattern. So to do so, we take the memories available in the technology and we create a banked memory subsystem that then we tell the high-level synthesis tool is a new memory with, for example, 16 ports that can access 16 words at in the same cycle. So now the high-level synthesis tool has the ability to perform different optimizations when it runs the scheduling, because it knows it can access 16 elements from memory at the same time. So this is, and obviously we not only create the RTL of the memory, but we also create the corresponding view for the high-level synthesis tool. So this is all transparent to the user. The user just needs to specify how many parallel accesses are necessary. And then everything else is automated. So you don't really see the interface. But in reality, if you opened up the generated RTL, you would see the same interface that you have with the normal SRAM. So that's the kind of interface you have with the private local memory.
Yeah, very good. So later on, Paolo will give an example how from the skeleton all this gets generated, and it will become very clear practically how they having a lean interface between the data path of the accelerator and the private local memory plays a key role to gain good performance. So the skeleton will be clearer later.
Yeah. Paolo,
so
we're already 45 minutes into the.
Yes, I know. So I'm going to move quickly to the next section and start with the tutorial. I just wanted to briefly show the socket of the processor that at the moment can host the two different cores, RISC-V Ariane 64-bit or the Spark Xeon 3. And again, here we leverage the standard bus interfaces and the same type of platform services that we have in the accelerator tile. Now, in this case, obviously, we need a little bit of customization for interrupt, for example, because that is a very processor-specific component. In the memory tile, we have the partitions of the last level cache, and we have the other portion of the DMA controller that allows us to access directly a DRAM controller, if available, or a link that goes through FPGA. Now, what we see on the right of this slide is all of the available coherency models that we can allow an accelerator to operate with, and that will be explained during the last demo in our tutorial today. So the accelerator may use the optional private cache and so be fully coherent with the system and just operate like any other core. It can be coherent with the last level cache, and in this case, it means that the accelerator runs really a DMA request that is, however, handled by the last level cache. And this can obviously save a lot of energy because you are not going to access memory every time you run DMA requests. You can go just non-coherently. So this is the most traditional option, for example, for streaming accelerators that don't use much locality. And then you have a final coherent DMA version without the private cache, which is an hybrid of the two. And really, it's very similar to the last level cache coherent kind of DMA, because requests are going to be handled by the last level cache. But it also allows the last level cache to recall data that are currently owned by other private caches. This is very useful if you have your third-party accelerator that needs to be coherent, but has no notion of the coherency protocol. And if you don't want, for example, to flash the caches in your device drivers. This, for example, can be used to run Ethernet, which is a component that requires full coherency, but at the same time, we don't want to flush the caches every time we need to swap the Ethernet buffers. And finally, the last option that we have to communicate is point-to-point. And this saves even more energy if you are able to create a chain of accelerators that not only share data in memory, but are able to operate in a producer-consumer fashion on the data tokens that are being written on a single store transaction from one accelerator to the other, rather than from one accelerator to memory. This also allows you to perform a much finer granularity of synchronization between accelerators rather than accessing memory, because you can synchronize them not at the level of an invocation, but at the level of a single data transfer. And obviously, this can increase your throughput if your application is creating a long chain of accelerators and working, for example, in batch mode, where you process multiple frames, for instance. So let's now move to our tutorials. And the first one is going to be an HLS-based flow using System C, and in particular, using Stratus HLS. In this slide, you see what we're going to do, basically. First, we are going to run an interactive script that generates a skeleton for the accelerator. Then we're going to customize it based on the code that is available on the webpage of ESP. So you can just cut and paste the code from there. I'm going to briefly discuss it and tell you what each line means and why we have modified the skeleton that way to implement that code. And then we will generate RTL using HLS. This step, if you do not have licenses for the HLS tool, you won't be able to run it, but you are able, if you want to follow us, to create the accelerator skeleton, customize it, and run the simple execution, like the simple simulation in System C. And then we'll show you how to generate the wrappers in ESP and how to integrate it into a full system. So let me switch right away to the shell here. And let's start from the beginning. I'm going to start from showing you, this is the web page. I can copy the link in the chat. If I can see, where's the chat? I don't see the chat. Here, you see it.
You don't see it? Maybe Davide can.
No, I have seen it now. Yeah, I've seen it now. Okay.
Anyway, if you just go to the ESP website under documentation, you can click on this tutorial.
Okay, so this tutorial is a very simple one, and we're going to implement an accelerator that performs multiply and accumulate on a set of vectors. So we assume our vectors are represented as a matrix. So there's a certain number of MAC vectors, each of a length, MAC length. And then we have our output vector, which is the accumulated result of accumulating every single vector. So we're going to have MAC VEC total accumulated results. Now, if you were just to code this in C, this would be just a simple loop where you run the accumulation on every single element after, of course, initializing to 0 the accumulation result. So the first step is to run the ESP initialization script. You can use the exact same parameters that you find in this web page. I'm going to change slightly the name of the accelerator and the ID of the accelerator because to be able to skip some of the steps and run through the tutorial faster, we have already generated the MAC, so I cannot regenerate another accelerator with the same name. So I'm going to use a slightly different name, but you can follow the tutorial as it is on the page and use MAC and 053 as the ID. So first of all, enter the root of the ESP folder and then run utils scripts init accelerator. So you see that the first thing you need to provide is an accelerator name. I'm going to call it my MAC this time. Then you have to select the type of HLS tool that you want to use. And in this case, we're going to use Stratos HLS. So we just use an S. Now the script asks you to tell where's the ESP path. If you are running the script from the root of ESP, that is already the correct path. So you can leave the default. Now we have to enter our unique ID, and I'm going to use 054 instead of 053, but you can use 053. This ID needs to be unique in your system, otherwise you're going to have troubles when you load the device drivers, basically. And then this is a step which is the most important of the configuration, where the user needs to specify the configuration registers of the accelerator. So how are we going to program this accelerator? So this is a simple one, so we don't have many registers. And we've said we're going to have a MAC length register, which is going to define the length of our vectors to accumulate. Now for this one, we can specify a default value that is going to be used in the skeleton of the user application that we generate to program the accelerator. Now in this case, we can say, by default, we're going to accumulate vectors of size 64 elements. Now the script also asks you to specify the maximum value that this register can take. This is very important because based on this maximum value, especially for this particular accelerator, the script is going to compute the size of our input data set and accordingly generate a private local memory that can hold the minimum data token necessary to process your algorithm, to make your multiply and accumulate be able to run through the entire vector. So let's say in this case that at most our vectors are long 100 elements. Now we need to specify the second register. And in this case, we're going to call it MAC VEC. And this is going to be the number of vectors that we want to process. So let's say that our default value of vectors is also 100. And the maximum value is 100 as well. So by default, we're going to run all the vectors that we have, that we can process in batch. Finally, we are going to define another parameter that is not part of the algorithm this time, that we call MAC-N. And this one is going to be our batching factor. So yes, in a single invocation, we want to accumulate 100 vectors of size typically 64 and maybe at most 100 elements. However, we may also want to say sometimes save some invocation time. So you don't want to invoke through the device driver your accelerator every single time. And if you have more than 100 vectors, which is what we say the accelerator can process in one single invocation at most, we can tell the accelerator, you know, after you've processed this 100 vectors, there's another batch of 100 vectors. So it's another multiplication factor that we can add in. And in this case, we can say that the default value is 1. So by default, we don't work in batch mode, but we may want to have up to 16 batches of this data set. And then we're done. So we have no more registers. And so the scripts move on to the configuration of the PLM. So first thing we need to tell the script is what's the bit width of your data token. Are we talking about integers, floating point numbers? It depends. So let's say in this case, we're talking about integers. And so we're going to use 32-bit default as the data width of the bit of the data token. And then we need to enter the input data size in terms of configuration registers. This is different from the bit width. This is the size of a single transaction of data that you want to do before starting computing. So for instance, if you want to be able to invoke your accelerator and with a single memory transaction, accumulate all of the elements in all vectors, this will have to be mech length, so the length of one vector, times the number of vectors that you want to process in this invocation. And remember that these are configuration registers, so these are not constants. When you invoke your accelerator, you'll be able to specify within the range between 1 and the maximum value that you select how many vectors and how many elements per vector you want to execute. So with this, the script computes the maximum size of your input data set. And that determines how big the local memory needs to be, because we want, again, in a single memory transaction to be able to bring in that many data and run them with high parallelism in your data path. Same goes for the output. Now, remember that this is a multiply and accumulate, so the output will just be the accumulated result. So if we process mech_len times mech_vec elements, we're going to have just the number of vector defining the size of the output. And again, the script computes the size of the output local memory. Now, we need to specify if we are okay with having memories this big. Now, in this case, the memories are not so big, so we can allow the script to generate a local memory that can hold the entire data set. But in many occasions, you might need to split this into multiple chunks. And so here you have the opportunity to tell the script, I know that's my maximum data set, but please load a quarter of it in a single memory transaction, do partial computation, and then load the next quarter and keep going. So here you have the option to specify if you want to run in a single transaction or in split transaction. Now, in this case, we can let it run with a single transaction because we know the memories are not going to be too big to fit on a chip. And so now we know exactly how our local memory looks like, at least in terms of size. Finally, we need to add, if any, if there is a register that determines what's our batching factor. And in this case, we're going to use this mech_n as the register that determines how many inputs we want to process on a single invocation. So before, when we defined the input and output data size, we were talking about single memory transfer. In this case, instead, we're talking about single invocation from the device driver. And for every invocation, we may have multiple memory transfers occurring. Okay, so our skeleton now has been generated. So if you now move to the accelerator folder, which is going to be ESP, accelerators, Stratus HLS, then we can open our folder, my Mac, which will be Mac in your case. And then we go into the source folder and we see that there's a bunch of files that have been generated. The complete list of files generated is listed here on the web page. So there's all the files required to specify the accelerator and run high-level synthesis on it. There's going to be a software folder dedicated to the accelerator here where we define bare metal application, Linux application, and device driver. Now, the bare metal and Linux application are almost complete, but we need to add the two functions that generate the input data and validate the result. And then finally, you see that for each of the Lean 3 and Ariane, we have a few headers defined that allow the basic ESP device driver. The ESP device driver is common to all accelerators that we design through these flows. And that will allow the ESP device driver to discover the accelerator and to set the configuration registers that are not user defined, but that are part of the socket. For example, since we're handling virtual memory, the device driver will have to set the base address in the socket of the memory buffer that gets allocated for the accelerator to process data. So back to the HLS folder, you'll see that there's a source folder, which is the one I've just opened. There's a Stratus HLS folder with the HLS script, which is ready to use. You may even not open this script and it will run fine. And then the test bench folder. So we need to customize two things here. One is the mymac.cpp, in which you have the load input and the store output function already implemented for you, following the specification that you gave with respect to the data set size. And they are also flexible in terms of the width of your memory. For example, if you select to implement this into a system which has a 32-bit architecture processor, it will assume the DMA and the coherence and the cache coherence support bit width is 32-bit. But if you select instead a 64-bit architecture processor, it will assume that the DMA width is going to be 64 bits. So this is already implemented for you. And you may need, of course, to customize it in case you have more complicated transactions to implement. But what we're looking for really is the compute stage, which is the only one that really requires customization. So in the compute kernel here, I'm going to try to increase the size of this one. So in the compute kernel here, you see that all of the registers have been defined as variables. There is a standard section here in which we wait for the configuration, and this is all handled by the ESP driver, so it's transparent really to the user. And when this configuration occurs, the value of the configuration registers implemented inside the socket is transferred into the variables that then you can use to implement your behavior in the computation kernel. And your behavior, which by default here is going to be implemented in the skeleton as an identity function, should be implemented starting from this point. So after you see the compute comment is where you want to insert your code. So let me go back to the web page and show you the code that we have to insert here instead of the one that you see. So this is the accelerator behavior. So what we're doing is, first of all, we need to know what's the input length in this case. So the input length, again, we said it before, we defined it in the script, is the length of a vector times the number of vectors, right? As opposed to the output length, which is just the number of vectors that we have. Then we add a bunch of variables that you use just for housekeeping, to remember where we are in terms of how many vectors we have been processing, the vector number, and if our memory, in case we chose, for example, to chunk our memory, if our memory cannot hold an entire vector, where we left in terms of index in a single vector. And then obviously we have to initialize our accumulator. Then down here we have the loops that go through the size of the local memory, which in this case is perfectly with respect to the size of the data set, but it could be different. So, you know, this is adding a little bit of flexibility when you want to process vectors that are larger than your PLM. And that's why we're showing you this here. And then once you are in the body of the loop, with respect to what you see in the skeleton, instead of applying the identity function, we look again on the input length which again was transferred from the configuration registers. And then we simply accumulate the multiplication of even elements times odd elements, where we assume that the even elements are the coefficients and the odd elements are the input data in this case. So we take two elements of the vectors, we multiply them and accumulate until we reach the end of the vector. In fact, you see that this internal loop is incrementing the index by 2 every time it loops over it. When we reach the end of the vector, it's time to write into our output memory. And so here's where you see the write to the output memory. Now, one additional thing that the skeleton generates for you, and that here we have expanded with the implementation of the multiply and accumulate, is that it already provides the implementation of the memory as a ping pong buffer, meaning that it's going to split your computation into multiple memory transactions, because you have to bring in, for example, if you set your batching register not to be 1, you have to bring in multiple chunks of data. You compute them, you store them back, and you store them back to memory once you have the result. Now, if you use a ping pong buffer, what you can do is you let the load function, which has been implemented for you, run and bring in the next chunk of data while you compute. And then you let computation run on that new chunk of data while the store function that again has been implemented automatically store back the results of your first computation. And so the ping pong buffer here allows you to pipeline computation with load and store operations. The way we synchronize this is by means of these handshakes, which are functions that have been generated with the skeleton. So in each section of the code, load, compute, and store, you can call these methods, which are either, like in this case, compute load handshake or load compute handshake, or again, compute store handshake or store compute handshake. And basically, these tell you that we are either requesting to push some data or to pull some data, or we are acknowledging that we received that data. And so we're basically releasing the producer that can go ahead and fetch the next chunk of data. So this is how we synchronize load and store with the computation so that they can use the ping pong buffer and never overwrite data that have not been consumed yet. And again, the primitives are generated for you, and you can choose where to place them. So every time this block execute compute load handshake, it's basically telling the load function that it can go ahead and fetch in the next portion of the ping pong buffer the next chunk of data, because the first one has already been consumed. So we take this code and we copy it, if I'm able to with the screen, sorry. We copy it into the, okay, this is going too fast. Okay, we take this code, we go back to the shell, we paste the code here, and we remove the pre-existing code, which was implementing just the identity function. Obviously, you may also choose to modify a little bit this code and play with it. So this is the only thing that needs to be modified inside the source function of the multiply and accumulate. Now, the next thing you need to edit is in the test bench. And so we move to the test bench folder. And in particular, we open the main file of the test bench, which is system CPP. This test bench is modeling the entire final system. So it's modeling the processor core that configures and programs the accelerator, as well as the main memory with which the accelerator communicates and shares data with the processor. So here, go back to the web page, we're going to look for the initialize input and compute golden output functions, which are the only two things that we cannot automatically generate because these are application specific. So here's where we compute the golden output, and here's where we initialize the memory. So we take that code, and we replace it again. And how do we initialize it here? Well, in this case, we've chosen to do something like this. For each element of the vector, we just use the index of the vector modulo the number of vectors that we have. And this allows us in this simple example not to have an overflow of the integer variable. Of course, you can use random inputs. You can choose any other ways to implement this initialization. And the golden output is really just implementing the simple algorithm that was shown in the beginning of the page. So it's computing, multiplying, accumulating software, basically. Okay, so this is going to be here. And we don't need these two loops anymore. And that's it. So now you have a complete test bench to run your unit test, to run high-level synthesis and test the implemented RTL of your accelerator. Now, these changes that I've just made on the test bench, the exact same ones, have to be done as well for software. So let me move just 1 second back to the root of ESP and show you where the software for the Mac has been generated. So we're going to go to soft. You can choose either a Leon 3 or a Yan. Let's say we go on the Leon 3 folder for now, drivers, and then you'll find the My Mac folder. So in here you have the Linux application marked as app, the bare metal application, and the device driver. The device driver is already complete because you've specified the configuration registers, and so we were able to generate the complete device driver. The bare metal application requires the same edits in your function where you validate the buffer and where you initialize the buffer that was just made. The only difference is that the test bench that you've seen before in System C was C++, and this is plain C. So that's why the code is slightly different. If you go in the web page, you'll find that code in the section Accelerator Integration. Here it is. So it's exactly the same loop that I've shown you before for the test bench, but again, it's implemented in C rather than System C. So you just need to take this one and replace the init buff function with the code. And again, you can initialize with random, from file, like you wish. Well, in bare metal, not from file. I don't recommend that. But in the Linux application, you may even initialize your code from file. So this code is going to be good as well for the Linux application. So we move to the Linux application folder, open the mymac.c, and then we see the exact same init buffer function, although this application will run in Linux, and we copy it here as well. Okay, and we delete this one. So with this, we've finished implementing our simple accelerator and unit tests. So if we move back to the SoC main folder, which is here, yeah. So you can select any FPGA.
Paolo, before we move back,
yes.
Also just a check on time for you. Meanwhile, let me see. I don't see any question on Q&A in chat, but if I remember correctly, you have finished modifying the skeleton of the accelerator to make it specific for this particular application. So from now on, there's no more modification of the code.
Exactly.
Now, from now on, there are high-level synthesis and validation of the accelerator. Any question before Paolo moves on? Well, if there are questions, you can post it on the chat or the Q&A. Paolo, please.
Yes. Okay. So you can choose any of the available FPGA design flows. In this case, folder. Sorry. In this case, we are going to synthesize for the Xilinx VCU 118 evaluation board. And from here, what you can do after you've sourced your environment is run your HLS. So for example, you just run make mac HLS. And this is going to first generate the memories and then run Stratus HLS. The first time you run this step, it might take a while because HLS has to generate the resources. Here we've run it for you before. At the same time, you can run, for example, the execution in plain system C of your accelerator and check if you've implemented it correctly. So here's just checking that the software implementation of Mac corresponds to the system C implementation of Mac. Also, after you run a basic configuration of ESP with, for example, ESP dev config, you will be able to compile your application. So the first one that you can compile, for example, is the bare metal one. And you can do make Mac bare C. This compiles the bare metal application. And the bare metal application then is going to be available here in the design folder inside bare C. So these applications here can be used for full system RTL simulation, as well as for FPGA bare metal simulation. You're going to use the executable that is going to be converted into a file that gets loaded by the memory model and simulation. And you're going to use the binary to load the program in main memory before booting the system. Also, you could compile your Linux application. However, before we do this step, we need to create the Linux environment and the root file system on which the application is going to be copied. So we can do so by simply typing make Linux. And I recommend you not using plain J, but select a number, of course. I would say at most 8 if you don't want to use all the memory you have in the system. So this is going to do a bunch of things. It's going to compile the kernel for the target processor that you have selected in the ESP configuration. And in the next tutorial, you're going to see the GUI and how to configure the system. It's going to compile all of the device drivers, both the ones that are common, so the ESP device drivers and API, as well as the device drivers that you've added for your own accelerator. So it's going also to compile our Mac device driver. It's going to compile the applications, and it's going to create a root file system for you with not only everything that is required to run Linux, but also with the applications to test the accelerator. So once you run make Linux, you basically have an image that can be loaded into the FPGA, ready to test your components. So you see these steps can take a little while. So, and these are basically the conclusion of this tutorial. The only other step that can only run at the end of the high-level synthesis is to run the simulation of your accelerator in RTL. And as soon as high-level synthesis is complete, we can do so. But in the meantime, if you have any questions, I think this is the perfect time to ask them while compilation completes.
Paolo, for those that were not able to run the HLS tool, we should probably create some folders in the tech. So that
yes, all right, I almost forgot about that. While it compiles, one of the things that I can show you is if you do not have access to the high-level synthesis tool, but want to move to the system configuration, what you need to do is to go into the root of ESP and then enter the tech folder. And then, for example, we've selected the VCU 118. So this is going to be the Virtec UltraScale Plus technology folder. And you see here that we have an accelerator folder where things have been generated. For example, if we open the Mac folder, you will find that at the end of high-level synthesis, there will be an accelerator definition, this XML file, and then there will be one folder for each HLS implementation that we've run. By default, our skeleton is implementing 2 basic HLS implementations, one with DMA 32-bit and one with DMA 64-bit. So if you want to be able to run the next steps, but don't have high-level synthesis, the only thing you need to do is create these folders at these paths. So enter tech, Virtec UltraScale Plus Mac. Actually, you have to create Mac, and then inside the Mac folder, you can create Mac Basic DMA 32 and Mac Basic DMA 64. these are the only things required to be able to then configure the system in the GUI. Of course, there won't be RTL inside, so you won't be able to generate the FPGA model unless you actually run high-level synthesis, but at least this allows you to move forward.
And I want to add that we're also gonna use one of the accelerators that it's already in the ESP repository, which is FFT.
Yeah, so you would have to do the same for FFT.
So yeah, and those are the 4 folders that you need to create, so that then you can do the next steps even though you didn't run HLS.
Exactly. And in particular, let me just show you that once you have those folders available, you are basically able to run the ESP GUI. And in the drop-down menu, you will find FFT and Mac. And if you select Mac, for example, in the implementation menu, you will be able to select between the two. Now, in this case, we only have one.
For now, don't worry about the GUI. We will do that later, yeah. But this is just to show.
This is just to show, because this is basically corresponding to the current architecture, which is 64-bit. So if you do not have those folders that I've shown you before, you won't find Mac and FFT in the GUI. Okay, so HLS is still running, but I'm just going to show you the target and then hand over. If you run Mac-sim at the end of HLS, this target will run the simulation and verify your accelerator first in System C, but inside the environment of the high-level synthesis tool, and then run all of the RTL implementations that you have in your synthesis script. All right, so I'm going to stop sharing and hand over to Davide for the next section. Meanwhile, if you have questions, I'm going to take them on the chat. On the Q&A, sorry, on the Q&A section.
So the next question will be, the next session will be run by Davide Giri, who is a PhD student and has led the multiple projects within ESP, including on the whole reconfigurable memory hierarchy and the design flow for an integration of third-party accelerator like NVDLA. So this will be the first topic. Davide?
Yeah. So we will talk now about NVDLA as an example to describe our third-party accelerator flow. I will then go back to where Paolo left off. We will recap and then construct whole SoC. So don't worry if you were unable to complete all the steps and create those folders. We will go back to that. So in ESP, as you have seen in the initial presentation, we have a third-party accelerator flow. You can see it highlighted here. This is a picture that you have seen already. So now we're in part 2. For this topic, as usual, on the website you can find tutorial. This one would be similar. So click on it. Here you have the guide and all the information. So this is just so you know where to find all the information afterwards. Now, we said that for this tutorial we are targeting this FPGA. In ESP, inside SoCs, you have a bunch of supported FPGAs that you can choose from. There are 5 at the moment. If you were to target an ASIC technology, you should imagine to have a folder here for your ASIC technology, and then you run all the make commands from inside it. So we move inside this target for the VCU118, and we've already run HLS for the math accelerators. Now we need to run the steps for NVDLA. So first I'm going to show how to use NVDLA in ESP, and then I'll show you a little bit how we integrate it. So for NVDLA, all you need to do is move in your folder and launch a target called make NVDLA. This is going to do 2 things. It's going to generate the RTL for the NVDLA hardware based on a specific configuration. In this case, we are using the NVDLA small configuration. While this is running, I will take a second to tell you what NVDLA is. NVDLA is a deep learning accelerator from NVIDIA. It's a fixed function accelerator, but it's highly configurable. And you can configure the hardware to have different sizes. We go, in our case, for the small ones, so 64 Mach unit, 188 kilobytes of local memory. NVDLA, you can see at the bottom here, is a hardware IP, right? But it comes with a very complex, very complete, not complex software stuff. And what you need to run at runtime so that you can invoke in NVDLA is this part on red. So there's a user application taking some inputs, then there's a user mode driver and a kernel mode driver. Everything else that you see in blue is something that normally happens offline, and it's for preparing the inputs, the configuration for the user application. We have shown with ESP at CARV this year that we are able to construct SoCs with multiple NVDLA instances, multiple memory links, and we show that we can run some known neural networks, and that we can get a good scale up in performance by parallelizing work on multiple NVDLA. In the meantime, we compiled the software of NVDLA and we generated the hardware just with one simple make command. When you run this step, there is something that gets added to the root file system of Linux. Because we're going to test this with Linux on FPGA. So if you go in the sysroot folder, you will find in root NVDLA folder. So automatically, after compiling everything, the runtime library, some of the inputs get copied here. And one other thing that gets copied in the root file system is the OpenDLA driver, which is the device driver for NVDLA. So in ESP, every time you change anything in the root file system that will be in your Linux image, you have to recompile Linux so that you get a new image with the new file. This will take just 1 second. In the meantime, I want to show you how we integrated NVDLA. Really briefly, of course, we don't have time to see all the details, but what you do in ESP is you add your third-party accelerator as a folder in this third-party accelerator DMA64 path. DMA64 is for if you want to target a 64-bit architecture like the one we have with Ariane. For 32-bit architecture, it means that the accelerator will run in an SoC with the LM34. So what you do in the NVDLA folder in this case is, first of all, you need to create a make file, which is actually what we invoked when we ran make NVDLA. In this make file, what you need to do is to make sure that if you run make all, you're going to compile all the required hardware and software of your new third-party IP. So in this case, you see that with the target software, we are compiling the user mode driver and the kernel mode driver. With the target hardware, we are generating the Verilog of the specific configuration of NVDLA that we are using. You can see here that we are pointing to some paths in this very folder, IP, software, and out. This is because in this folder, where you see IP, where you see software, these are literally the repositories of the software and hardware of NVDLA. So they are submodules of the ESP repository. And then output points to the generated Verilog inside the IP folder. A couple of other things that you do is to generate a Verilog drafter just to link the interface of the NVDLA to an interface known by ESP. This is just about wires and eventually setting some default values for those wires that are a mismatch between the interface. And then finally, we have a list of files. For example, of all the files you need to be either compiled or copied in the root file system. So, for example, NVDLA Verilog contains the list of all the Verilog files of NVDLA, so that ESP can find them. And then another example that I can show, there's multiple ones, but for example, in UMD, let's look at UMD, which stands for kernel mode driver, we have the path of the driver so that we can copy it over automatically. So this is the idea of how you integrate the IP into ESP very briefly. In the meantime, we have compiled Linux. So interestingly, this is all you need to do for the accelerator integration in ESP. Later on, actually in a couple of minutes, when we try to configure the SoC, you will see that we will have the option to include NVDLA as a file in the SoC. And from there on, it's all push button, and we will then test everything on FPGA. So this is all you need to do for NVDLA. I want to go back 1 second to where Paolo left off, because now we need those generated files from HLS. So what Paolo showed is that to run the high-level synthesis and generate the Verilog for your accelerator, you run make HLS. We also said that we want to use one of the already available accelerators in the ESP repository. It's called HFT. So you would be launching the make HFT HLS. After this run, you cannot run them because you don't have the HLS tool. So I'll show you what would happen if you were to run them. The tech folder of ESP, as Paolo showed, because we are targeting the DCU 118 FPGA, there will be something that gets generated in the Virtex Ultrascale Plus technology. Especially into the accelerator folder, you will find FFT and MAP. Now, for those of you that are repeating these steps, Paolo already told you, but I want to make sure you have the time to actually create those folders. You need to go here, create folder called MAP, a folder called FFT, and then inside them, you need to create these two folders and the first two that you see here, called FX32. If you give a different name, it's not a big deal. Just make sure that you have the FFT in the name and DMA64. The DMA32 or DMA64 at the end is important because it's telling us that this accelerator is for a 32-bit architecture, so it can only be instantiated with the Leon 3 core. This is for a 64-bit architecture, so it gets instantiated with Ariane for 64-bit architecture. Okay, so
there is a question.
Yeah,
can I use ESP to generate fully unrolled hardware for existing DNNs? Let's say if I have a pre-trained mobile net model from TensorFlow, can I generate fully unrolled hardware RTL from that TensorFlow model? I think we'll answer this question when we do the flow ESP for ML, no?
Correct.
So just let's be patient a second, and the next segment will be answered.
We have a tutorial specifically for that where we use HLS for ML. It's not developed by us, but a tool that takes your TensorFlow and automatically generates an accelerator for with Vivad HLS. Okay, so in the meantime, you probably all generated this. So we get to the point. Let me go back. Now we finally get to the point of working with the SoC flow. We'll then later go back to the accelerator design flows to present 2 more flows that are really interesting. Of accelerators designed at a higher level from the system C1, because they are in Keras, for example, or C++. Now in the SoC flow, what I want to show is how you take all these IPs that we generated and integrated and put them together to design your own SoC and then test it in simulation or on a FPGA. So for this purpose, I need to open a graphical interface. So I'm working remotely from very far with my connecting to my computer in New York. So I'm using X2Go now to open the GUI. We are still in the same folder. Basically, if you want to work with an FPGA, you almost never move out of this folder and you launch everything from there. So what we want to do is to configure an SoC. So make ESP access and configure. This launches the beautiful ESP GUI. It starts to be dated. And we configure an SoC. Now you should follow the steps that I'm doing in the GUI. We do a 4x3, so we change the layout to make it bigger. And we want to instantiate 2 NVDLAs. Then we place 3 FFTs. As you can see, for FFT, we have 2 different implementations from the HLS tool, so you can choose. In this case, we do the 32-bit version. And notice that I have selected the Ariane core, so I can only see the DMA64 option. If I switch to Leon 3, then NVDLA disappears because it's not meant for a 32-bit architecture, and here I can only see the DMA. Okay, so NVDLA. Finally, the IO file. Okay, so this is the layout we're going to work with, and testing, simulation, and then an FPGA. After you're done with it, you select the Ariane, you have all these tiles, you can generate the SoC and close. Okay, after this step, there are some files being generated. You can see the file .espconfig. Basically, it contains all the information from your GUI. So here you can see the 12 tiles, a couple are empty, we have FFT, NVDLA, and so on. There's also a SoC map file being generated. This one contains information on all the memory mappings in the SoC, IPD indexes, APD indexes, and so on. So at this point, literally, we did everything with the GUI, and from now, the system is ready to be deployed on FPGA, or the system is ready for full system simulation. ESP has generated everything that we needed in terms of interfaces, NOC routers, tiles, and the whole SoC. So for going the FPGA path, you need to generate an FPGA bitstream. Simply, you can launch make Vivado scene, and this will create the Vivado project and run everything down to the bitstream generation. Of course, this takes a while, so I already have the bitstream ready. Here you see it's in the Vivado project. For the full system simulation instead, for the simulation we run bare metal programs. So there is one default program that gets run if you don't specify anything in particular, which is the unlock from ESP program. But in this case, we have accelerators in the SoC. So we want to run a simulation of the unit test application that you prepared with Paolo, the bare metal application that you prepared with Paolo. To do that, we can launch make sim to launch a simulation, and then we can specify what bare metal program we want to run. So in this case, It's the MAC-Exe program. Whenever you want to compile your bare metal program, you do make name of the accelerator and .c. So this compiles your bare metal program, and it will be found, and you can find it in the .c folder locally. So, as I said, of course, this step of simulation you cannot do it because you need the CAD tool. If you in ESP you can use model sim by using the command make sim. You can use Cilium with the XC-sim, and you can use Incisive with NC-sim. Those are the three ones we support. You are welcome to patch ESP to support more of those tools. When you launch the simulation, the first thing being done is that all of the RTL gets compiled. Of course, there are a lot of files because it's a big SoC. But there's one more thing that happens even before compiling. In another window, I'm going in our DC118 folder, and you can see that there is a SLD gen folder. This is all code RTL that gets generated by ESP based on what you specify in the GUI. By the way, SLD is the name of our research group, so that's why the name. In this SLD gen, in particular, there's a lot of stuff being generated for the accelerators. So there is an accelerator tile file that is multi-purpose. It can instantiate any of the available accelerators based on a generic being passed with a parameter. And then we have the wrappers, the tile wrappers for all the accelerators that we have in our system. And again, this is all automatically generated. So I just wanted to show you what's happening under the hood. So since I launched the simulation, after compiling, we are inside model sim. Now this is in batch mode. And if we do run all, we can run the simulation. Full system simulation takes a few minutes. So instead of doing this, I will show you later on FPGA the same program, the same bare metal program, but running on FPGA. So you can see the expected output. But we will just do run A, and then the simulation will run. I also want to mention that if instead of sim or NC-sim or whatever I showed earlier, if you add GUI, the same simulation is launched, but not in batch mode. It will open the GUI mode.
Yeah, it's worth mentioning, Davide, for when you create a new accelerator, the moment the accelerator is available in the technology folder for the particular target FPGA, you can run, for example, Mac Sim, Mac HLS, Mac Clean, Mac BRC, and all those make targets are automatically inferred by ESP, so you don't have to specify those targets. As long as the accelerator is available, meaning as long as you completed the previous step of creating the skeleton and running high-level synthesis, then you can run those targets, and those become available automatically.
So, for example, I did make BRC, but another target available is make BRC clean, sorry, to clean it. And there's more. If you do Mac clean, you're cleaning the HLS step. If you do, there's also Mac driver, which is compiling the device driver. This is the Linux application, Mac app, and for all of these you can clean. By the way, the driver and the Linux application, they automatically get compiled when you compile Linux. You can compile them with a specific target, but if you don't do it when you compile Linux, we compile all of them and we add all the application executable and device drivers into the file system. Okay, so now with the I'll wait for this, and then we finally go into some FPGA prototyping.
So while we are waiting for this, maybe I could highlight one thing. to link a little bit what Paolo showed when you showed the design of a new accelerator and what Davide just showed with respect to the integration of different components. When you see that when Davide integrated with the GUI, he chose the certain size of the matrix of tiles, and in this case was a 4x4, didn't have to fill the whole matrix. Sometimes you do, of course, but and for in particular for an accelerator, when he chose the FFT, he could choose among different implementation of the FFT. Now today we don't have too much time to go into the details of how you can use a high-level synthesis to produce many different implementations, each providing a useful trade-off point in terms of performance versus cost. And having many different implementation make that accelerator more reusable across different SoC design. One thing to say is that the moment that we select one particular implementation of an accelerator inside the GUI, ESP takes care of adapt all the interfaces to that particular implementation, or to say better, the socket of ESP makes sure that independent from the implementation, the accelerator works correctly. Of course, with respect to performance, your mileage may vary depending on the particular trade-off performance versus cost that you may have chosen.
Okay, so for the FPGA, we need a couple of things. The first is to program the FPGA. Now, in ESP, in the local make file in your design folder, in this case for the VCU118, there are a few parameters that you can set based on your setup. For programming the FPGAs, these are the two variables that you want to set. You have to specify the host to which your FPGA is connected. If it's connected to your laptop, you can say just localhost. And then the port of the Xilinx hardware server. In this case, I already set them for my case. Another thing that we need to do, because we want to see the output of what gets run on the SoC on FPGA, is that we connect to the UART of the FPGA. Again, if the UART is connected to your own machine, it's easy because you can just open Minicom on your machine, or if you're on Windows, you can just connect quickly to the UART. If the FPGA is connected on a remote machine, with ESP you can specify the IP of that machine and the port, so that you can use a target that we will use in a second. That is make UART, and it will remotely connect to the UART of the FPGA. So to program the FPGA, after specifying those two variables that I showed, you run make FPGA program. Of course, you need to generate the bitstream before this. In the meantime, I'm also launching the other command I mentioned, which is make UART. And this opens Minicom connected to the VCU118 FPGA in our lab in New York. Then after programming the FPGA, we're going to first run some bare metal programs, the one that you edited with Paolo for the Mac, and then maybe also the one for the FFT accelerator. And then finally, we will put Linux and test NVDLA and a couple more things. So similarly to how we did MakeSim, now we are doing make FPGA run for running the bare metal test, but we need to specify what bare metal test we want to run. In this case, it's, for example, the map. Let's switch to something else, and then I'll show this later. So another SoC that I wanted to show is with the Leon 3 core. So in this case, I moved into the VCU128 FPGA. It's a different FPGA, just to try a different FPGA. However, this is FPGA has the Virtex Ultrascale Plus technology as well. So the accelerators that we have already generated are already available, are also available for this, and so we can find them in the drop-down. In this case, I want to select the Leon 3 core, and I want to enable the cache hierarchy so that beside the level 1 cache of the Leon 3 core, we will have a level 2 private cache in the CPU tile, and there will be some last level caches there will be a last level cache in the memory tile. For this SoC, we can do a 3x3, where what we want to do is to have 4 cores. And in this case, we do some accelerators as well, but we do FFT, so that then we will show some nice experiments with multiple FFTs running in parallel. Then we place a memory tile and an IO tile. When you're missing something, ESP tells you, for example, at least one IO tile. Another thing that I want to do, since we have multi-core, I already did it in advance, but by default in ESP, often the Linux multi-core, Linux SMP is disabled. I want to enable it in this case. So now also for this new design, our GUI is ready. We could run the bare metal simulations, but instead we're going to do the test on the FPGA. Just 1 second. Programs, and then we launch our bare metal. In this case, we instantiated some FFTs, so we can test it. So specify the program, make FPGA run. I didn't mess up the configuration. Okay, so this one ran. There's quite a bit of printout. I want to go through them because there's something interesting. So first of all, the bare metal test identified 3 different FFTs in our design. And the bare metal test is going to repeat the same test, the same unit test on each of them. So you see FFT0, then there will be FFT1, and then FFT2. What it's doing for each of them is running a unit test where they get invoked to work on some inputs, and then the bare metal test validates the output. You see here, this is where the accelerator starts. Here is where the accelerator notifies the processor of being done, and then the validation can pass. What's different in each of these invocations that you see here is the cache coherence mode with which the accelerator tile is working. In the first case, is non-coherent DMA, so what you see here with these probes are the caches being flashed to be able to work non-coherently. Then we have LLC coherent DMA, where only the private caches need to be flashed. And then we have coherent DMA and fully coherent cache, where we don't need to flash anything. So these are the tests that we have executed in bare metal, 12 tests for per accelerator. What I forgot to mention when we were doing the configuration, of course I generated the distance in advance, but when I did that, I selected this option as LP. Only with this option, the fully coherent mode can work, because it requires the accelerator tile to have a cache. So that's what the test is doing in the fully coherent cache asset. The accelerator is communicating with the cache, which is communicating with the rest of the cache. Now, on this big screen, I also want to show a nice application that involves working with multiple accelerators. For this one, we need to launch Linux, and to be able to compile this application, we need to run the target make examples. This is because we placed the application in the folder top examples, and especially it's the multi-FPGA test. So whatever test or application we place there gets compiled with make examples. And then, as usual, I've already done it, but as usual, we copy over the folder into the root file system. And finally, every time we modify the root file system, we want to compile it. Okay. So I already have the image ready. And with make FPGA run Linux, we are not only launching Linux on the system on the FPGA, but before that, we are also programming the FPGA, because make FPGA program is a dependency. Now, every time you see that I'm launching something on the FPGA, you see this ESP link. The way ESP works is that in the I/O tile, there is a debug unit which is connected to an Ethernet port. And to start a new design, to start a program or to start a boot on the SoC on FPGA, my host machine is communicating through Ethernet to the debug unit of ESP. And the things it's doing is it's sending the binary of the program to be executed, and then sending a reset to the processor core so that the processor core can start. So actually we are sending two binaries, because the first one is the bootron, basically it's a bootloader, and then the second one it takes a bit longer, and it's the Linux. Normally there would be a bar loading. So what we see now in the Minicom, in the serial interface, is that we are booting with 4 cores. You see 4 CPUs. So this is full-fledged Linux. At the end of the boot, we get a lease for an IP. Because with ESP, Linux also has Ethernet available. So with an ESP instance on FPGA, you're able to do SSH into it, or SCP copy files into it through Ethernet. That's why you see that we have the list of an IP. Another important thing is that you see some device drivers being registered. In fact, in this case, we are registering, this is not really device driver, it's a single one, but a driver for the caches used for flashing them. And then you see 1, 2, and 3 instances of the FFT accelerator. We log in into Linux, and in the examples folder that I added, we compiled and added, we have the multi-FFT application, and I will run it first and then describe what it's doing. So the first test is running FFT accelerator, only the instance is 0, with non-coherent DNA. The second one is involving the same accelerator again, but with a different type of interaction with the cache hierarchy, which is called LLC coherent. You will see the details in the last part of the tutorial. Then we launch it a third time with the fully coherent DNA, which is the one that requires private cache. And then there's 2 more tests. This one is interesting because we see 3 different accelerators, all working with a different type of cache coherence. All the 3 types that we tried so far, all working at the same time on the same SoC. So literally, we have our user application spawning 3 threads and invoking in parallel 3 accelerators. Finally, one other nice feature that Paolo mentioned, we have in ESP, is that we can chain the execution of multiple accelerators so that the output of the FFT is sent directly to the next FFT in this configuration to the network on chip without going to shared memory. So this is a direct point-to-point link of 3 accelerators. And this is configured at runtime. So in your application, you can specify if and how you want to do this connection. So this is interesting because it's showing all these different features. So I'll go back to where I stopped in the previous tutorial. It turns out that connecting from Europe remotely with the Minicom wasn't working. So now I have a new setup. I just want to show one final thing. If you remember, this was the setup. We have 2 NVDLAs. I already have here I programmed the FPGA and I copied everything, copied the Linux image over. So here in Minicom, we can see the boot that terminated. You can see 3 FFTs being registered, 2 Mac accelerators, and 2 NVDLAs. Now I moved into the NVDLA folder and I just want to show you the NVDLA running, and in particular I'm gonna copy and paste here a command to invoke 2 different instances of NVDLA. Okay, you can see that I invoke the NVDLA runtime 2 times. One time with instance 0 of NVDLA and one time with instance 2. This is a patch that will add to the NVDLA software so that you can run and invoke multiple instances in parallel. I compiled the software without the verbose flag, so there will be a lot of prints, but you can also compile without the verbose, and that's better when you want to record the execution time because it doesn't print a lot. See here it's doing everything twice because it's 2 different instances. The prints you see right now are from the device driver, the ones with the timestamp. The ones without the timestamp are from user space. This is doing LeNet with 10 layers doing NIST, and you can see that both terminated with the test part. So this was just to show NVDLA, and then with the other SoC I already showed you how to do instead unit tests in bare metal and with Linux for your accelerators with ESP. So this was just to complete that part.
So now we go and talk about the design flow for the application domain of embedded machine learning. Davide?
Yeah. So as you can see, we go back to our driver figure for the tutorial. We now show how we integrated the use of a tool called HLS4ML into ESP, such that from a Keras, PyTorch, or Onyx specification, you can get automatically the generation of an accelerator, but not only, we also get the integration of that accelerator into ESP, all done automatically. On top of that, we even generate some unit test, bare metal application and Linux application, and the Linux device driver. So like it's a full automatic integration. So here I think it's we are definitely going to give a shout out to the HLS team, HLS4ML team. I just want to show you where you can find more about the HLS project, where as you can see from a high-level specification, they get an HLS project, they got HLS, and then finally an accelerator. The HLS4ML is developed by the customer lab. Actually, Giuseppe has been one of the contributors to this. And they also have a nice website with a lot of information. I highly recommend you to take a look at this project. Okay, so for this part, instead of doing a live presentation, I'm actually going to show a video of a hands-on tutorial, which is pretty much, it's part of the video that we already have uploaded online, and it shows you what type of, it's an example of what type of hands-on tutorial you can find online.
Hello everyone, In this tutorial,
let me know if you're hearing the sound. Okay.
Yeah, we are hearing fine. How long is the video, Davide?
The video is, I will play about 10 minutes.
You may interrupt if necessary, if
Yeah.
there are questions or things like that. So let's monitor the Q&A in the chat. Let's go.
Tutorial, I will show one of the ESP accelerator design and integration flows. This flow leverages a tool called HLS4ML that is able to automatically generate an accelerator starting from a Keras, PyTorch or Onyx model. With this flow, then ESP automatically integrates these HLS4ML accelerators into a full SoC, and we will go all the way down to deploy the SoC on FPGA and test it. There's a written version of this guide as well
Davide,
on our website.
I think you need to stay on the video.
You read there what are the prerequisite tutorials and go over them before getting started with this one. You will also see that we provide some pre-built material so that you can try the experiments without having to go through all the steps of the tutorial. Mainly in this tutorial we will have a first part where we use HLS4ML to generate an accelerator. HLS4ML generates accelerators in C++ for the tool Xilinx Vivado HLS. And then in the second step we will move into ESP, and with an interactive script we will import this accelerator generated by HLS4ML, and we will automatically integrate it and test it into ESP. As a first step, we clone the ESP4ML repository. For the purpose of this tutorial, we will be using a Keras model already provided in this repository. So we can move in. You need to install the tool. I've already done it, so I'm not going to run it, but this is the command. Then we move into the example models. We're not going to build a new model ourselves. We're just going to generate one here. You can see from Keras config that the default model is a 3-layer. This is a 3-layer multi-layer perceptron. It's just 3 fully connected layers. In our case, we do want an input and an output. These are not provided, so we provide them on the written guide on the website. You can go on our website, you can go and download them there. We provide very short inputs and outputs. It's only with 8 inputs and 8 outputs. And what you're gonna do is you're gonna fetch them wherever you download them from. It's just these 2 files, and you copy them into this Keras folder. Basically, we took some input and outputs from a branch of this HLS4ML repository, and we just made them very little, very short. So now we're ready to convert the Keras model into a Vivado HLS accelerator. It's pretty fast. Now you see that you have a Vivado HLS project folder called My HLS Test. We're just gonna go inside and run. We're gonna run C simulation of this accelerator. Only the C simulation. Running the C simulation generates this C sim result log, which we're going to use because these are the results produced by the accelerator, already quantized with the fixed point precision of this accelerator, and we're going to use them to validate into ESP. Then this is it. So remember this path, because ESP will need to import this path. I'm already gonna copy it for later. Okay, now we can move into ESP. Here I already cloned it. You should go through the prerequisite guides, especially the setup guide, to have everything ready, the toolchain, the environment. Now to integrate an HLS4ML accelerator, we're going to launch our interactive script for generating accelerators. In this case, we're going to call the accelerator MLP 3 layers. Then we're going to choose the HLS4ML design flow. We're already in the ESP home, which is what I suggest. So for this, we keep the default. Here we can paste the path of the Vivado HLS project that we generated with HLS4ML. Here, this is a 3-digit hexadecimal. It's an ID for your accelerator. Here you can really insert any number that doesn't overlap with other existing accelerators. In the written guide, for example, we say 194. The only limitation is that in decimal, this number should not be bigger than 1024. Okay, the data bit width of this accelerator can be found going into this parameters file. So this is the data type of the accelerator. So it's 16 bits in total and 6 bits of integer part. So we could do 16 bits, but for the purpose of this tutorial we do 32, so we're actually wasting some bits in this case. But as long as this number is bigger than the precision of the accelerator, it will work. And you can choose between 8, 16, 32 and 64. As we saw a second ago, the fractional bits were 16 minus 6, so 10. Then we go back to this file and we can see that the first layer has 16 inputs and the last layer has 5 outputs. So input data size 16, output data size 5. And going back one more time, as I was saying, those input and output files that we moved around, they got transformed into these TB input features and TB output predictions. Each of them have the same number of rows, and as you can see, it's 8 rows. So we have 8 inputs for the test bench. Now this is done. This is all you need to do. Your accelerator is fully integrated in ESP, and from this moment on, all the steps are the same as for what we showed in other guides for System C accelerators or for C++ accelerators. So as usual, you move into a design folder. For example, in this case, we choose the VCU 118. I have here a little script to set the environment variables. You make sure you set them as described in the setup tutorial, in the setup guide. And now the first thing we do is we run the high-level synthesis for the Vivado HLS accelerator that we just imported. So this Vivado HLS project. The Vivado HLS project is now, by the way, into accelerators, HLS4ML. You see there is a folder MLP 3 layers, which has been generated by our steps. Here, all of these things are generated by ESP. So test bench, the scripts for HLS and simulation, source files, and this is an XML with some information needed by the system. Here are some header files, and instead this HLS4ML folder is nothing but exactly the content of the original My HLS project. So if you look at this content, you see build project firmware. If we go back to our project here, you can see it's the same. So this is just a copy and paste of the project inside of ESP, plus the addition of all these things for wrapping and interfacing the accelerator with the rest of the ESP system. So how do you run HLS with ESP? You just type the name of the accelerator, it will autocomplete, and then HLS. You can see first that it ran the C simulation with those input files and output predictions that we moved around earlier, and the test passed. So you see how this script not only imported the accelerator but also added a test bench that works automatically. Now this takes a while, and for all of these steps that take a while, I will just fast forward. Now, what does the HLS step generate? First of all, the whole project is running in accelerators, HLS4ML, name of your accelerator, and there will be an HLS work, and then this is the technology, Virtex UltraScale Plus in this case, of your FPGA. So that's the Vivado project. Then once Vivado is done, generated the RTL is placed in tech. Again, the technology of the FPGA you chose, and then in accelerator, MLP 3 layers. Here you have two versions of the accelerator. Inside there you find RTL. Example. Here you see the generated RTL. There are two versions because we always generate DMA with 32 bits and 64 bits, because the 32 bits will be instantiated when you use the Leon 3 processor, and the 64 bits when you use the Ariane processor. Now we'll see in a second. So now the accelerator exists, it's been generated, and it's in Verilog. We are going to configure an SoC with the ESPX config command. As I said, here when you choose Ariane or Leon, it will change your option for the accelerator. So here, of course, now we can find our new accelerator. You see it's DMA64. If I choose Leon, it goes to DMA32. Okay, so
this is the first part and the main part that I wanted to show for this tutorial. From this point on, as you may have understood this point, the flow doesn't change, and it's the same for all accelerators. So when you get to the point where your accelerator is integrated and you can allocate it from the GUI, then the SoC flow is all the same and is the one that I have shown. So this is it for this part, and in the next part I will leave control to Giuseppe. He's going to talk about the flow with Catapult HLS and accelerators designed in CC.
Yes, so Giuseppe Di Guglielmo is an associate research scientist here in the Department of Computer Science at Columbia, and he is an expert in computer-aided design, verification, and design of accelerator for machine learning. He's also one of the contributors of the HLS4ML project, and he's also an expert in high-level synthesis, and so he's going to talk about a new design flow that incorporates a different commercial high-level synthesis tool. Giuseppe?
Thank you, Luca, for the introduction. I have pre-recorded this section of the tutorial, so I can also answer your question online, both on the chat or the Q&A. Let me share my screen and the audio sound, let's see. Do you see it?
Yes, I see it.
Welcome to the fifth section of our tutorial on ESP, an open source platform for agile system-on-chip development. In this section, we will illustrate how to design an accelerator with the C++ flow of Mentor Catapult HLS. Please note that Catapult HLS supports, as design specification languages, both C++ and System C. In this section, in this part of the tutorial, we will describe some aspects of the C++ flow and the integration of the accelerator in ESP. We are working on the Catapult HLS System C flow and its integration with NVIDIA MatchLib. The material that I will present in this section is also available as hands-on tutorial on the ESP webpage. We choose the softmax function as a running example for this section. In machine learning, softmax is a widely used activation function that usually you find at the end of a deep neural network because it turns scores, floating point values, into probabilities. The sum of the output values is 1. The softmax function outputs a vector that represents the probability distribution of a list of potential outcomes. For example, if your neural network is a classifier, it may tell you if the image that you are passing as an input is a mug or a pencil, the probability of being a mug or a pencil. You can also see the formal definition of the softmax here. It takes as an input a vector and returns a vector of floating points values. We choose to leverage an open source implementation of the softmax as it is provided by Mentor on hllslibs.org. This implementation uses piecewise linear approximation and algorithmic C data types, Mentor ACFix. The input and output arguments of the function are parameterized so that the arithmetic can be performed at the desired fixed point precision. This allows the HLS designer to trade off among area and performance. In this section, we will not explore the capabilities of the HLS tool for design space exploration, but we will focus on the accelerator interface, its general structure, and the integration on ESP. As a preliminary example, this is how you would use softmax function from Mentor in a generic design. I want just to highlight how the function takes as an input arrays, use ACFix as data types, and that you can choose the precision of the input and output values. You can find the material of this section on the ESP webpage. The material contains the HLS project and the software. The HLS project is the C++ code, the test bench, and the Catapult HLS scripts for the softmax accelerator. We will focus mostly on this part during the tutorial. The software is the application and device driver for the accelerator. Apart from minor code edits and console commands, you are not required to explicitly code, but we invite you to review the provided code and scripts when you will try it at home. To begin with, let's download and decompress the tutorial material. Make sure to do this operation in the ESP root folder, so all of the files will be extracted in the right location. This is the ESP root folder. Let me get the URL to the tutorial material. I download it and I uncompress the package. In the next slide, we will see where this file has been unzipped. Which location actually this file has been unzipped in. We adopt some naming convention for the accelerator that we design with Catapult HLS. We use the _CXX suffix for the accelerator from the C++ flow, and we will use the _sysc suffix for the System C accelerator. In particular, the name of the accelerator for this tutorial is softmax _CXX. If you have correctly uncompressed the material in the ESP root folder, the files for the HLS project will be in the directory accelerators Catapult_HLS softmax 6XX, while the software will be placed in soft Leon-free driver softmax and soft Ariane driver softmax_CXX. Now, you have to know that Leon-free and Ariane mostly share the same code. This is why for the Ariane software, we have mostly symbolic link to the files in the Leon-free directory. For the next slides, I want to introduce a classification for accelerators. In particular, accelerators can be classified accordingly to how they couple with the processor and the memories. There are two main classes of accelerators: tightly coupled accelerators and loosely coupled accelerators. Tightly coupled accelerators sit in the CPU proximity. They usually share CPU resources. It could be the register file, the memory management unit, the caches. There is no overhead for the invocation. And they are virtually transparent to the software. On the other side, they require an expansion of the ISA to include special instruction to manage their operation. As well, this ISA expansion usually percolates to the software via the compiler or through low-level libraries. This kind of accelerator, tightly coupled accelerator, usually pose time enclosure challenges. This accelerator logic must usually meet the same clock frequency constraints that are set for the CPU. And much more, they may have limited portability across different system designs. The second class of accelerator is the loosely coupled accelerators. This has a greater area budget. They cannot degrade the CPU performance, and we are able, with loosely coupled accelerator, to tailor their local memories. Much more, we can move data between the accelerator, the private caches, last level caches, and DRAMs. The ESP accelerator follow this second model, the loosely coupled model. Much more, the accelerators are integrated in a ESP instance as devices managed with Linux device drivers. The ESP accelerator operates on large datasets, and they alternate computation phases with data transfer phases. The interface of an ESP accelerator has ports that are common across all of the supported HLS flows, as shown here in the figure. And in particular, there are only some minor syntactic sugar differences between all of the HLS tools. And we will see them in a couple of slides for Catapult HLS. In particular, the port in a ESP accelerator allow to communicate with the CPU via memory map registers, this confinfo port, and to program the DMA controller. We have a couple of ports for read and write operation. Then we can transfer data from and to the main memory via this DMA read channel port and DMA write channel port. Finally, there is a port to notify the completion back to the software application that can be mapped to a register or to an interrupt. In this case, we can see the actual code that you would use with Catapult HLS, and in particular with the C++ flow. You may notice in particular that here, this is the C++ interface. Here we are using mostly AC channel, and there is also an AC sync. In particular, AC channel allow the accelerator to transfer data to and from the top module. And these data types, when is combined with the HLS directive CCS in wait, ensure that the data is properly synchronized at the interface via latency-insensitive protocols. We will see how ready and valid signal will be added to these channels. And indeed, when when Catapult HLS synthesize the interface, we'll add the proper handshake signals to the RTL netlist. The AC sync channel is a synchronization channel from Catapult HLS, and it offers the possibility to specify a standalone handshaking. There is essentially no data transfer, it's just an handshaking signal, and here is paired with this directive CCS sync out valid. In addition to this interface and this directive, these data types and directive, we have also to specify some user-defined data type, and in particular we have data type for the configuration register that are memory map. In the case of a softmax, we have only one register, the batch, the size of a batch. Then we have data type to specify the DMA configuration, while the configuration of a memory map register can be defined by the user. Usually the DMA configuration cannot be defined by the user, is common to all of the ESP accelerator. And in particular, here you can find an index for that is used to specify the memory offset of the DMA access and the length of the DMA transaction. There is also a field size here that is mostly to encode the DMA width. Finally, the user can specify the size of the DMA word, which can be 8, 16, 32, 64, etc. And this will extend, will apply to the rest of the ESP system. After HLS, post-HLS, this is how the interface look like. You may recognize most of the ports that we have defined here. Essentially, we have all of the ports, all of the data port has been appear here with the underscore dot suffix, and we have additional signals for the latency sensitive protocol. In particular, you can see the ready and valid signals. Let's have a look to the synthesis step. In particular, let's start from the source directory. Here, if you remember, we have unzipped the material for the tutorial, and in particular, the HLS project ended up in this directory, Accelerator, Catapult underscore HLS, softmax underscore CXX is the C++ version. And source basic is one of the two architectures that we are designing. Here in this directory we have the source code, and you will recognize here at the very beginning of this function the interface that we have just seen for an accelerator, for an ESP accelerator, and in the particular case the softmax accelerator. You may recognize the AC channel for the data transfer and the AC sync for the notification. This is just a synchronization at the very end when the accelerator is completed. We may want to run synthesis. This usually is done in the directory ESP system on SoCs, and here we have a specific board that we want to target. The command for the synthesis in this case is we make softmax CXX-HLS. Most of the flow is automatic, so after we have unzipped the file, the tool is able to recognize that a new accelerator has been added, and if the scripts for the synthesis scripts are properly written, some targets to make file are automatically added. Here in the specific case, we are also specifying the width of the DMA. We run synthesis. This may take a couple of minutes. And when the synthesis is complete, the ESP infrastructure will place the RTL, the generating RTL, in a specific folder. In this case is ESP tech, stay for technology, Vertex, ACC accelerator, and softmax CXX, etc. And the RTL file is this one, And in particular, again, here at the very bottom of the file, you may recognize the RTL interface, Verilog RTL interface for our softmax accelerator. We have seen the interface, how to define an interface for an ESP accelerator when you describe that in C++ for Catapult HLS. We want also to see what is the internal structure of an ESP accelerator. I want to remember you that an ESP accelerator is a loosely coupled accelerator, and in particular the accelerator execution consists of 4 phases. There is a configuration phase, and after a configuration phase the accelerator iterates over a load, compute and store phase. For Catapult HLS we have defined 2 different coding styles. There is the first, more simple block architecture. In this case, the phases run in a sequential way and are implemented in a single C++ function. We will see this in a couple of slides. And then we have a hierarchical block architecture. In this case, the phases run concurrently to one another. And in particular, to add concurrency, we combine, in this second case, HLS directives with a recommended coding style, while still leaving the C++ untimed and single-threaded. The synchronization between the blocks will be added automatically during the synthesis process. Finally, let me also stress the importance in a ESP accelerator of private local memory, PLMs. In particular, the PLMs allow the accelerator to load and store data, to interact with the external world, with the main memory in particular, via the DMA controller. We have input PLM, we have output in PLM, and we have additional private local memory when those are necessary. The most important part is that this PLM can be tailored to the needs of a designer. Sometimes PLM may be implemented as circular buffer, in some other cases as ping-pong buffer, this to reduce the latency and increase the throughput of the system. As well, very important is the number of ports that you can add to the PLM to keep the throughput with the logic, with the computational logic. We have defined 2 coding styles for the accelerator that follow the Catapult HLS C++ flow. The first one is the single block architecture. The main characteristics of this coding style are that the configure, load, and compute and store phases run in a sequential way and are implemented in a single C++ function. And the private local memories, the PLMs, are defined locally to the C++ function. You can see here a pseudocode for the single function. We will see in a second the C++ code, but this is just to give you an idea in a single slide. Here on the top we have the interface that we previously defined during the presentation. Here, at the very beginning of the function, we define locally the private local memories. Then we have the configuration phase. We are reading from the confinfo port. We collect the parameters, the memory map parameters that are stored on the confinfo channel. Then we iterate over the batch, the number of batches. This is the single parameter that comes with the softmax. We iterate over the load phase, the compute phase, and the store phase. A load phase consists in programming the DMA. Essentially, we are telling the DMA how much data we want to read starting from which offset in the main memory. Once the DMA is programmed, we can start reading from the DMA read channel. Again, the configuration goes over the DMA read control, and the data comes in the DMA read channel. Then we pass to the compute phase. Here we are leveraging the Mentor Catapult HLS library with the softmax function. We are using the AC softmax that we have seen at the very beginning of the presentation. When the computation is complete, we pass to the store phase. During the store phase, the very first thing that we do is configuring again the DMA. We want to store data in main memory, so we have to inform the DMA starting from which address in main memory we want to start storing data, and then we perform a final loop to send back the data to the main memory. This load, compute, store phases iterates over and over until we have consumed all of the batches. The actual code for the single block architecture is the actual code. The C++ code is essentially the same as the pseudo code that I've shown you in the slide. The main difference of the details that I want to stress here is the fact that it is necessary to explicitly enforce the serialization between the DMA configuration when we write on the DMA channels and the data transfer that this is true both for the load and compute phase. And this is true when you code the C++ implementation of the accelerator for Catapult HLS. Let me show you exactly where this is happening. It is here. This is when we configure the DMA. Essentially, we are writing on the configuration channel for the DMA reads, and we are doing this through a non-blocking write. We are iterating over until we are able to write on the configuration channel, and we are getting this return parameter done, and this conditional statement on this return parameter is the trick that we use to force the serialization between this DMA control and the following data transfer phase. If you don't use this little trick, what happens is that the code is not functionally correct. Essentially, the data transfer starts before the configuration of the channel has been completed. Here you can see the coding style that we have adopted for the hierarchical block architecture. In this case, the main characteristics are that the configure, load, compute, store phases are coded as separate C++ function, and the private local memories, the PLMs, are globally defined as shared among the C++ function. And in particular, Catapult HLS offers the modeling construct AC channel also to allow users to directly model the data exchange between blocks of hierarchy. And in particular, in software functions like the load, compute, store can exchange data via shared arrays or variables. But, however, this becomes problematic for HLS since the synchronization of data exchange between blocks must be inserted automatically by the synthesis tool. Because of the inherent complexity associated with this, Mentor Catapult HLS offers the modeling construct AC channels to allow the user to directly model the data exchange between blocks of hierarchy. And please notice that the user can use the AC channel class library both to model the I/O streaming, as here in the case at the top of this function we have a data input and data output from the block, as well to model the memory interface. Later on, you can see here in the function we are declaring the private local memories as AC channels, and these AC channels are passed as parameter to each of the load, compute, and store function. Finally, in this coding style, you may also note the use of AC sync to force the block synchronization. Here we have the config, load, compute, and store done signals that are passed as reference to the various process. And here at the very end, when all of the process has completed, we are collecting one by one these done signals, and when everything has been done, we return the accelerator done signal. As as arrays are become bigger in hardware, it is typical to map them to memories during the synthesis because of the area and power cost of mapping those arrays to register. The costs become prohibitive. And in particular, in Catapult HLS, mapping shared arrays between blocks to memories in a hierarchy design results automatically in a ping-pong memory structure. And this is kind of useful, and as we have seen, this is a feature really important for ESP Accelerator because it's one of the key being able to tailor the private local memory to keep the maximum throughput of the accelerator. Finally, in addition to the above coding style and directives, it is also important an additional coding style, and this must be followed to ensure that the extra memory are not inferred during the synthesis process. First of all, you have to remember to encapsulate the array, the shared array in struct, like in this case. And then a local struct with the packet array should be declared to perform the memory operation. This local struct is optimized away if the coding style is carefully followed. And for example, here in this case, we have the load and store function. In the load store function, we are here declaring this local instance of the memory. This is a local copy, and in this local copy, we perform the read operation. In this case, this data, DMA read channel, is coming from the main memory. We are reading this DMA channel, and we are updating the private local memory, this temporary copy, and only when all of the data has been stored in this local copy, we can force write back this copy to the actual private local memory of the accelerator. And it is still similar for the store phase. In both of the cases, if you follow up this coding style, this second memory will be removed, and there will be only one single shared memory between the top function, top hierarchy, and the load, compute, and store functions. We are getting close to the end of this section of the tutorial, and what remains to do after the design of the accelerator with Catapult HLS is to instantiate them on an instance of ESP. I open the graphical interface for the ESP configuration. You can see here my NOC. My screen is a little small here, but still I can distinguish the NOC. And what the very first thing that I want to do is to make a little more room. What I do is I move the I/O tile up here, and down here I want to place my two accelerator, the one that I have just designed. I want to create an instance of softmax, the basic one, the single block, and an instance of the softmax, the hierarchical architecture. Then what remains to do is to generate the system on chip configuration, and make Vivado scene. This will take a little. After this, my design will be ready. I will have a ready bitstream that I can use to program my FPGA. The material that I used during this section is available online and on the ESP webpage. It comes also with the software application and the device drivers to run your ESP instance with Catapult HLS accelerators, both in simulation and on FPGA. Thank you for your attention.
Now we have the last segment, which is a short segment that shows how we can use ESP to do research also on particular important topics of computer architecture. Davide?
Yes, I'll share with the computer sound so that you can play the video. Yeah, this is some work from a couple of years ago, but it's a good example of computer architecture research done with ESP. And it also shows a nice feature of ESP, in my opinion, that is the ESP monitors. You will see there's a nice GUI and nice monitor information extracted from FPGA.
In this demo, we are demonstrating on FPGA our work on reconfigurable cache coherence models for accelerators. There are three main cache coherence models for accelerators. The non-coherent model has accelerators bypass the cache hierarchy and do direct memory access to the DRAM. The last level cache coherence model, which we introduced, has the accelerators send their memory requests directly to the last level cache without keeping coherent with the private caches. Lastly, the more processor-like model is the fully coherent model, where all the accelerator transactions are kept coherent. The accelerator can either have a private cache or can send requests directly to the last level cache, and these requests are kept coherent with recalls. Our work, as well as other recent literature, shows that no model is the absolute best. The best choice of cache coherence varies at each accelerator invocation, depending, among other things, on the number of active accelerators, their memory footprints, and their memory access patterns. We designed support for all the cache coherence models, such that the coherence models are completely transparent to both the programmer and the accelerator designer. The cache coherence of each accelerator can be dynamically selected at each invocation. To confirm the potential benefit of all of this, we designed an adaptive algorithm that dynamically chooses the proper cache coherence model at each accelerator invocation. The algorithm is once again transparent to the programmer, and it makes introspective decisions based on the current status of the system. Now let's dive into the FPGA demo. First, we are loading a bitstream of our SoC on a Virtex 7 FPGA. This script first deploys the bitstream on FPGA and then loads Linux SMP and starts the boot, which we will follow in this other window through Minicom. In the meantime, we're going to launch on a host machine a monitor GUI, which collects live statistics from our system on chip on FPGA through an Ethernet link. Here we're just showing some of the data graphically, but the monitor data coming out of the SoC is really useful to perform architectural exploration directly on FPGA. By taking a look at the monitor GUI, while the multi-core boot completes on FPGA, we see that on the top left there's the SoC under test, which counts 2 memory controllers, 2 CPUs, and 12 accelerators. These are distinct synthetic accelerators with a wide range of communication properties. At the bottom right, we have a graphical view of the NOC traffic, but only for the 2 bidirectional DMA planes. The router-to-router links will be colored to indicate the amount of traffic. Once logged into Linux, we launch a synthetic application and then launch the data collection in the monitor GUI. If you look at the terminal on the left, you'll see the LLC argument, which means that in this case, all accelerators are running in last level cache coherent mode. The second argument, none, means that we are letting Linux choose freely where to allocate memory. The application currently running is composed of 9 phases, where the first phases have at most 1 active accelerator at each time, whereas the last phases have up to 12 active accelerators. Phases also differ in the size of the workloads. As the execution proceeds, you can observe the NOC traffic in the GUI. And then once the execution will end, we will take a look at the final statistics of NOC traffic. By looking at average and max, we can see that more traffic went to the memory controller at the top left and that many NOC links have not been used at all. Now we will re-execute the application by enabling our adaptive algorithm. Notice the auto argument in the terminal. And with the second auto argument, we are also enabling some policies for better distributing the memory allocations across the two memory controllers. These policies do not affect performance significantly in this case, but we will see clearly a much better distribution of the traffic. As a first result, in the terminal, we can see that the per phase execution time is decreasing. And we can also notice how many more NOC channels are used and that the traffic is spread out more evenly across the SoC. We can now look at the average and maximum NOC traffic, and we see how it's really spread evenly across the SoC. Here are the results after running the application with two other baselines. All accelerators non-coherent and all accelerators fully coherent. Our adaptive algorithm, represented by the first bar, reduces both execution time and off-chip accesses. To conclude, this experiment was able to successfully exploit the cache coherence reconfiguration capabilities of our architecture, and all of this is transparent from the point of view of the programmer. Thank you very much for your attention.
Okay, so this was an example of architecture research with ESP, and now I'll start this for Luca.
Yeah, let's wrap up. We are coming to the close to the end of the tutorial. So first of all, we hope that this gave you a good introduction to ESP. This slide is just to highlight that we have been using ESP to do the design of several SoCs that then we have used to perform a variety of experiments that ended up supporting contribution that we have reported in our scientific publications. And these there are 4 examples that you can check out, and you're invited to check out the papers. So then in conclusion, in summary, I guess what we want to say is that we contribute ESP to the open source hardware community in order to support the realization of systems, if you move the animation, which are more scalable, have more scalable architecture. For SoC, they integrate more heterogeneous components, and thanks to a more flexible design methodology, which accommodates different specification languages and design flows. So the flexibility of the methodology should be clear, hopefully, to all of you. ESP was conceived as a heterogeneous integration platform from the beginning, really, several years ago, and has been tested through years of teaching and research at Columbia University. So in conclusion, our message is that we hope that you find ESP interesting. We hope that you want to use it for doing your own research, and also that some of you may want to contribute to ESP in terms of components or in terms of tools, so both in terms of architecture as well as methodology. Next. So here, of course, you can go to the ESP webpage or the webpage of our group, and there is a variety of publications that give you much more detail on ESP. And in thanking you, with the last slide, the ESP team would really like to invite you to register for one of our channels, or more than one. We have a Twitter channel where we report major new features that we release as part of ESP. We continue to contribute to ESP. And of course, we have a YouTube channel where we put some of our videos in support of demo or for particular talks. So here on behalf also of Giuseppe, Davide, and Paolo, whom I thank myself, we want to thank you for your attention. And unless there are some final questions, I think we are finishing 1 minute, 2 minutes late, but we are on time. Thank you. We want to thank Dimitris, of course, and the whole team that supported us in from a logistic viewpoint with delivering this tutorial. I think we can stop the recording now.